Hello again, I am Pedro Masudi, consultant of Geostatistics at Geovariances. We will have a series of webinars about the application of geostatistics in mineral resource estimation. It's the first webinar and it's somehow an introduction to the importance and the application of geostatistics and why it is important in the estimation of mineral resources. So the main challenge that geostatistics try to answer is how to generate a reliable and a robust estimation of mineral resources. So the main question is the estimation of mineral resources is the main challenge that we want to cope during mining geostatistics. Now consider that we have a set of drill holes. Here you can see on the map view. The distance between the drill holes is 100 meters in the areas where we have dense drilling, and it can reach to 1 kilometer in places where we have less dense drill holes. And imagine that we have a block size of 75 by 15 meters. Here I have a profile that I want to show you. This profile AA prim. I have an envelope, the envelope of the green, the envelope of red and the envelope of blue. And the goal is to interpolate the grade and the iron grade between the wells where we don't have the wells. So a classic method is the nearest neighbor. All of you are aware of these basic methods. If you apply nearest neighbor to interpolate the grade value in the space of the blocks, we will have a shape like this. The colors show that we have a big impact of some isolated samples to a large area, which might be somehow irrealistic, and also the artifacts or that you can see the pixel shape or rapid changes, which are because these methods are quite basic and cannot reproduce the continuity that exists in the data set, because such classical methods doesn't take into account the spatial variability. So regenerating or generating the continuity of your deposit in the space of the drill hole, in the space of the blocks, is a little bit challenge. If I use another classical method, which is inverse distance, again, you all are aware of the inverse distance. The theory is quite simple. Usually we can have a better continuity between the wells, and usually we have less artifacts. Still, we have artifacts in, I will show you in another example, when we apply inverse distance, and still we have the problem of the continuity. Another big issue is that in the inverse distance we have a power to define what should be the power 1, power 2, power 3, or a bigger value. We don't have any clear indication or guidance about the power of the inverse distance. Of course, that those who are experienced, they have some ideas, but it's still very subjective. And the method that we want to show you or to discuss about it mostly during the especially during the third webinar, because this webinar is introduction. Next one is mostly variogram and the necessity of data analysis, and the third one would be about the method of kriging that I'm presenting it here to you. When you apply the kriging method, because it's based on variogram, usually we can have a better continuity, or the continuity is more respected than the classical methods, which is very important for mineral resource estimation. In addition, kriging not only gives you the map or the 3D model of the resource, but also gives you this information, which is the uncertainty of interpolation, we call it the standard deviation of Kriging error, or simply we can call it uncertainty of interpolation. This uncertainty is minimum in presence of the samples, and it's maximized where we are far from the wells or where we are doing extrapolation. So later we'll use such quantities in order to do mineral resource classification that we will talk about the help of geostatistics in classification of mineral resources in the fourth webinar. Let us take a look at the result of grade-tonnage curve. If we apply the cutoff of, what is this cutoff? 67. The cutoff of 67 is applied to the curves which are created based on nearest neighbor, inverse distance, and kriging. We can see that the total tonnage based on the method of nearest neighbor is 750 megaton. Based on inverse distance is 570 megaton. And based on the method of kriging, it's about 514 megaton. And the difference you can see is it's quite big, 46% between the nearest neighbor and kriging, and 11% between inverse distance and kriging. So it is something important, and we cannot ignore the choice of methodology in order to estimate our resources, because as you can see, it will have a big impact on all the decisions. And the kriging, one of the main advantages of the kriging is that it is based on variogram. Variogram is a function that describes or quantifies the variability of your grade as a function of distance. In fact, when we are going to interpolate at the point of star is an undrilled or unsampled data location. We will apply some sort of averaging, weighted averaging, based on the neighboring samples. The first question is that, do I have the right to include, for example, this sample, which is very far from my star location, to this interpolation or not? So it's the question of neighborhood. And the second question is that what should be the weight attributed to each point which is in the vicinity of the star location. Again, kriging method is based on the variogram. What is variogram? For constructing the variogram, first of all, we compare all the couples of the samples. So let us compare 0 and 1. Let us compare sample 0 and 2, sample 0 and sample 3, sample 0 and sample 4. When we compare these pairs of the samples, there is a measure of dissimilarity, which is one of them minus the other, power 2 divided by 2. We calculated it, and we expect that as a function of distance, the dissimilarity increases. So those pairs of the samples that are farther, statistically, generally, they will have more dissimilarity or less similarity. And we will do this exercise for all the pairs of the samples. We will have such complicated map, which we call it cloud variogram or variogram cloud. And in order to understand what does it mean, what is the meaning of this cloud variogram, we will synthesize it in a curve. The curve that synthesizes cloud variogram is called experimental variogram, which shows or quantifies the increase of dissimilarity as a function of distance between the samples. So it is a very important, it's a key issue, and it's something like a heart of geostatistics or heart of kriging, which defines not only the variability, but also continuity, of course, because continuity and variability, they are inverse. Let us see what is the impact of continuity on the variogram. Consider we have 3 images. These 3 images, they have the same average, they have the same histogram, but we cannot distinguish them based on classical statistics. But variogram helps us in order to distinguish between these three images. How? The image on the right, the phenomenon, it can be a grade, it can be a geophysical measurements. It's very continuous. And the variogram starts from 0 up to some value at, for example, the distance of a range of 15. On the right, there is no spatial structure. So we call it nugget effect because the variogram shows the maximum variability at all the distances. But as you can see here on the right, where we have strong spatial continuity, the variability is quite zero for the short distances and increases as the distance increases. And in the middle, there is another image. It shows the presence of spatial continuity, but it is less continuous as the image on the right. So the rate of increase of variogram is higher in the middle than in the right. So as you can see here, variogram reflects the spatial continuity or variability of our phenomenon. Kriging is an interpolation method. It tries to interpolate based on two criteria, being precise and being unbiased. Of course, that we want to have unbiased and also precise interpolation, and we don't want to have a precise interpolation even if it is a biased interpolation, even if it is precise, or an unbiased interpolation, even if it is even if an imprecise interpolation, even if it is unbiased. And it is the worst case that we can have in interpolation, imprecise and biased. So the goal is to have these two parameters. And how do we use geostatistics in order to um, have precise and unbiased estimator, which is called Kriging. We talk about it in our training courses, about mineral resource estimation, or MRE, that I will talk about them at the end of this lecture. This is another example. It's a plan view of a iron example. It's a pedagogical case study. That if we apply nearest neighbor, inverse sum of power 2, and Kriging, you can see that the results are quite different. The nearest neighbor results in some geometrical shapes which shows abrupt changes. Of course, it is not realistic in the mineral resource estimation. In the geology, we are sure that we don't have such geometries in the earth. The second one, in inverse distance, still we have the problem of continuity. The bodies are discontinuous, and again, we are not sure we are quite sure that it is not a good estimation. So we have some artifacts related to the neighborhoods and related to the this power that is sometimes very difficult to find out the right power. And the Kriging, which seems to be more realistic because it's based on a variogram, and the variogram, the combination of variogram and nugget effect makes our deposits quite smooth, that we can handle it in a better way. In addition, Kriging not only gives us this result, but also it gives us the error of measurements. So the error of measurement, or the error of interpolation. The error of interpolation is minimized at the sample location and is maximized between or at extrapolation areas. That will help us later in order to classify the resources. And of course, we have some other tiny issues that could be taken into account by Kriging, like, for example, information effect. In fact, the data that you collect, they are at the support or at the size of the cores. But the information that we need here in order to do to design mines and to do production decisions should be on the support of SMU or selective mining units. So how to change this support? We talk about it again during the trainings, and also based on the software Isatis.neo that we promote. You can simply calculate the block kriging from the points from the data which are collected at the support or at the volume of the cores. Geostatistics provides several methods for evaluating or for modeling continuous variable like grade, density, porosity, permeability, etc. We have a bunch of linear methods like kriging or co-kriging. Co-kriging is simply multivariate version of kriging that takes into account two or more variables if you have. So it's important to use co-kriging when you want to reproduce the correlation or the relationship that exists between your variables at the drill hole. Like for example, if you're arsenic and if you're gold, or for example, if you're silver and gold, they have correlation in the drill hole space, and you need to generate it at the block space. So we are obliged to use some multivariate methods like co-kriging. Again, we talk about them, these linear methods in the mineral resource estimation course. And we have some nonlinear methods that I will talk about nonlinear methods during the webinars number 5 and 6, like geostatistical simulations and uniform conditioning, and also MIK and the other methods that are interesting, especially in the first phase, at the beginning of exploration, in the early phase of exploration, when the spacing between the drill hole is quite a lot, so the continuity between the wells could not be reproduced correctly based on linear methods. So the linear methods had their own application, the nonlinear method, they have their own applications for continuous variable. And for a categorical variable, like for example facies or mining domains, we have some other methods like for example indicator kriging, or a potential field method specific in the Isatis.neo software, or some nonlinear methods which are very powerful like PGS and SIS methods, also MPS method. The MPS is very interesting for example, if you have some patterns like the meons, or if you have some mushroom shape or batholiths that you want to reproduce them on your in your block model. Or PGS is very interesting for managing the neighborhoods. So if you have the neighborhoods and the neighborhoods are well known, it's possible to consider them in this method. And also the potential field method is a quick method that you can pick some points in order to produce for you the DXF file or the mesh file of your facies. Let us open Isatis.neo to have a demo on it. It's the Isatis.neo software that you can see. I have several projects here, ongoing projects. I will open today a new tutorial, which is tutorial mining. I will call it for webinars. As you can see here, we have a 3D view. This 3D view is quite sympathetic, and it's easy to work with the data and the blocks. I uncheck the blocks to see better what are the composites. The composites and the value of the composite are here. I can add, for example, the coordinates, or it's possible to add the compass in order to find ourselves. Where's my compass? Excuse me, it was here. I didn't see it. Yes, it's my compass. We have some shortcuts to look from top or look from, for example, east. It's quite easy and quite simple to work in 3D scene. And also it's possible to, if you have, for example, the block model, it's your block model with the ordinary kriging which is applied. I can simply cut it and see what is happening inside. We have different views for cutting. For example, it's possible to uncheck clipping for the drill holes like this using a manipulator. I can walk inside my deposit and see what is happening inside, and whether my interpolation corresponds to my drill holes or not. I've also a slice mode. In the slice mode, I can add, for example, a width of 50 meter, and it's possible to align the, the grid, or for example, along U, along V, in this direction, or along the W to have a plan view. I uncheck for the moment the clipping. Maybe I can show you also another function that we have. It's very nice and I like it very much, especially for reporting. If I want to report, always I put myself in orthographic view, and also I can define a fence. This fence helps us to create a kink section. So I can define my section based on several clicks. So consider that I want to have such complex section, and extension is important because in the extension it defines where are my drill holes. If I show you my section, it's a section that I'm going to produce based on the drill holes and the composites and the blocks. Simply I click on create section, and here you are, it's my section. Because I chose a very long section, it's better to add some Z scale in order to see what's happening inside. So 5 times vertical exaggeration plus all the coordinates that I like always to have an idea where I am in my deposit, and also the pick points 1, 2, 3, 4, 5, 6, 7 pick points. So it's a quite user-friendly software, even if it's very complete. In the first tab, we have the home, import and export. It's very compatible. It's compatible with, for example, Datamine, Leapfrog, Vulkan. We don't have any problem in importing or in exporting the information, so it's very useful. In the data management, as you can see here, we can create grid, we can create selections. It's possible to do compositing. If I show you the compositing, which is quite complete, we have some tooltips that helps you in order to understand what are, for example, what does residual means, what does, for example, compositing based on density, or compositing based on domain mean. Or in the next step, I can show you, for example, we have the definition of the lens and composite, and also I can show you here the second tooltip that we have, for example, the definition of minimum analyzed lens. What does it mean and how can we choose it? And the different options that we have uh, for managing the residual. In advanced mode, we have even more possibilities by some if phrases, if clauses. So data manager is quite complete about all data preparations and application that you want to do. And the statistics, it's something that we will discover together in the next webinar about EDA for variogram, for histogram. For histogram, I can quickly show you how can I produce the histogram of, for example, iron. It's like this. It's quite easy. And it's possible to apply some selections, for example, inside my rich ore or inside my poor ore. What is the statistics and histogram of my iron? We have some hierarchical sampling clustering, which is combined by the distance and the spatial aspect, which is very interesting in the Isatis.neo. In the third webinar, I'm going to present you Kriging, that you can find it here, and in the fifth one, MIK, and in the sixth one, simulations.